For a long time, people have speculated about the possibility of life on other planets. Thanks to the James Webb Space Telescope, the most powerful telescope ever built, that question might finally have an answer. Recently, while observing the closest star system to Earth, Proxima Centauri, which is only 4 light-years away, scientists detected unusual anomalies from one of its planets, Proxima b. These anomalies, referred to as artificial lights, have puzzled top scientists. But what do these lights mean? Could they indicate the presence of intelligent life on the planet? Join us as we explore the James Webb's surprising discovery of city-like lights that could change everything we know about extraterrestrial life. So far, Earth is the only planet where life is known to exist. Since the dawn of civilization, humans have wondered if life exists elsewhere in the universe. To investigate, American astronomers Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence, SETI project in 1984. This non-profit effort seeks to gather radio signals from space, as radio waves can travel great distances and are easier to detect. The Allen Telescope Array, composed of 42 radio telescopes in California's Cascade Mountains, has been listening for such signals for decades. However, after more than 30 years, no definitive signs of alien life have been found. The successful launch of the James Webb Space Telescope, JWST, has breathed new life into the search, allowing scientists to study distant, previously unseen planets orbiting faraway stars. The JWST, positioned 1 million miles from Earth and equipped with highly sensitive instruments, is key to this research. 20 years ago, no planets were known to exist outside our solar system. Today, over 4,000 exoplanets have been discovered. According to NASA, the universe may contain trillions of exoplanets. The first signs of life beyond our solar system might be found in extraterrestrial plant life. When NASA's Galileo spacecraft was en route to Jupiter, it turned its instruments back towards Earth and detected a clear sign of life: plants. The spacecraft identified the vegetation red edge, VRE signature, a combination of red and infrared light reflected by plant life. A planet like Earth, covered in forests, would have a strong and easily detectable VRE signature. The JWST will measure the VRE of distant Earth-like planets located in the habitable zones of stars, offering potential clues about life. As starlight passes through the atmosphere of an exoplanet, the JWST may be able to detect it via spectroscopy. The missing wavelengths in the starlight could be analyzed to determine the chemical composition of the planet's atmosphere, revealing whether it could support life. Earth-like planets with atmospheres made of oxygen, nitrogen, and carbon dioxide would be prime candidates for habitability. In addition to organic life, the JWST could identify signs of technological life. For example, chlorofluorocarbons, CFCs, used in refrigeration and cleaning products, are human-made compounds that would be visible to an alien observer studying Earth's atmosphere from a distance. If the JWST detects CFCs in a planetary atmosphere, it would be a strong indication of advanced civilization. However, life on exoplanets may not resemble life on Earth. Extremophiles, microorganisms that thrive in extreme conditions, demonstrate that life can adapt to harsh environments. Some extremophiles survive at temperatures as high as 250 degrees Fahrenheit 121 degrees Celsius, or in environments with highly acidic pH levels. While planets like Earth may be more likely to support life, it's possible that life could exist in extreme conditions too. Earth-like planets are more likely to support life if they have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is a yellow G-type star, but it is relatively rare and has a shorter lifespan compared to red dwarf stars, which are more common in the universe. Red dwarfs also have longer lifespans, providing more time for life to evolve. One of the JWST's first targets is the TRAPPIST-1 planetary system, located about 40 light-years from Earth. TRAPPIST-1 orbits a quiet red dwarf star and has 7 Earth-sized rocky planets, 3 of which may have liquid water on their surfaces. Despite the star being much smaller and cooler than the Sun, the proximity of the planets makes them prime candidates for the search for life, including possible city-like lights. Proxima Centauri, another red dwarf star, is 4.25 light-years from the Sun and is much fainter. For a planet to support life, it must be much closer to Proxima Centauri than Earth is to the Sun. In 2016, astronomers discovered Proxima b, a planet with a mass 1.3 times that of Earth, located in the habitable zone of its star. This Goldilocks zone is the perfect distance for liquid water to exist. While it is possible that Proxima b is an airless, barren planet, it also receives enough sunlight to maintain temperatures similar to those on Earth. Proxima b is believed to be tidally locked, meaning one side of the planet constantly faces the star, just as the Moon always shows the same side to Earth. Proxima Centauri is only 18% the mass of the Sun and shines much less brightly, yet liquid water could still exist on Proxima b if it has an atmosphere to retain heat. However, Proxima b faces challenges that make it less hospitable for life. Its proximity to the star means it is bombarded by strong solar winds, which could strip away its atmosphere. Additionally, it experiences significant temperature extremes due to its tidally locked nature. Nonetheless, scientists remain hopeful that future observations using the JWST will reveal more about this mysterious planet. Could the artificial lights observed on Proxima b be evidence of intelligent life? While it's too early to draw any conclusions, the JWST's observations open up exciting possibilities in our ongoing quest to find life beyond Earth. Proxima Centauri b, due to its proximity to its host star Proxima Centauri, is constantly bombarded with high-energy radiation, including X-rays and ultraviolet light. This intense radiation, particularly during stellar flares, bathes the planet in energetic particles. Without a protective magnetic field, similar to Earth's, these conditions could make Proxima Centauri be inhospitable to life. However, certain circumstances could still allow it to be a more habitable world. Models suggest that tidally locked planets like Proxima Centauri b may face atmospheric collapse due to volatile gases freezing on the permanent night side. On Earth, volcanic activity replenishes the atmosphere, and planets with strong magnetic fields are better at retaining their atmospheres. But since we don't yet know if Proxima Centauri b has volcanic activity or a robust magnetic field, it's impossible to determine whether it has an atmosphere at all. The presence of an atmosphere is crucial, as it would indicate the possibility of oceans, and together, these factors would hint at the potential for life. One compelling scenario suggests that if there is an advanced civilization on Proxima Centauri b, they might use solar panels on the dayside to generate energy to heat and light the perpetually dark night side, which would otherwise be too cold and dim to sustain life. The discovery of Proxima Centauri b has ignited a race to confirm whether it transits its host star from Earth's perspective. Such transits would allow scientists to calculate the planet's size, mass, and density, providing critical clues about its composition. During a transit, starlight passing through the planet's atmosphere could reveal details about its makeup. However, the chance of witnessing a transit is only about 1.5%, and the star's frequent flares make observations challenging. David Kipping of Columbia University explains that the heat from Proxima Centauri would cause a rocky planet to absorb sunlight and re-emit it as infrared radiation. Rocky planets give off a specific type of infrared signature when orbiting stars like Proxima Centauri. The James Webb Space Telescope, JWST, designed to study infrared light, is essential for observing this type of radiation. Detecting infrared emissions from Proxima Centauri b could help confirm the existence of an atmosphere. In theory, the JWST could even detect artificial lights on the night side of Proxima Centauri b, provided those lights emit within a narrow frequency band, fainter than Earth's own city lights. If the planet is covered with solar panels, they could reflect starlight as it orbits its star. Differences in temperature between the day and night sides of the planet would depend on whether Proxima Centauri b is barren rock or has an atmosphere and oceans. The JWST could measure this temperature difference over just 112 Earth days as the planet completes an orbit. If Proxima Centauri b does have an atmosphere, the next step would be analyzing its composition. Gases like oxygen, water vapor, and methane could indicate habitable conditions, or even life itself. However, detecting these elements requires capturing starlight as it reflects off or passes through the planet's atmosphere. A challenging task. Although the JWST is not optimized for finding extraterrestrial life, it can still detect changes in atmospheric concentrations of methane, carbon dioxide, and water vapor. Unfortunately, it cannot detect unbound oxygen, the strongest indicator of biological activity. Ground-based observatories like the Extremely Large Telescope (ELT), set to become operational in the mid-2020s, will be able to conduct more detailed atmospheric studies. The JWST could potentially detect substances like ozone, but future telescopes may take things further. Newer telescopes may use advanced techniques to block out the blinding light of a planet's host star, revealing starlight reflected from the planet itself, much like shading your eyes to improve your view of distant objects. This method could help future missions study planets in unprecedented detail. Despite these advancements, most gases released by life on Earth can also be produced by non-biological processes. Methane, for example, is emitted by both livestock and volcanoes. Sunlight also produces oxygen and hydrogen from water molecules through photodissociation. Thus, astrobiologists must be cautious about false positives when searching for signs of life. Understanding a planet's geological and atmospheric processes is essential to avoid misinterpreting potential biosignatures. The next generation of exoplanet research might finally deliver the evidence needed to prove the existence of life beyond Earth. The James Webb Space Telescope's initial findings offer a glimpse of the groundbreaking discoveries to come. Whether life exists elsewhere in the universe is one of the most pressing questions in science. It's possible life is widespread across the cosmos, or we might be completely alone, isolated on this singular planet in the vastness of space. Regardless of the answer, the implications, both philosophical and psychological, will be profound. The quest to find life beyond Earth continues to drive scientific innovation and exploration. Each new technological advance expands our understanding of the universe and the potential for habitable worlds beyond our own. While Proxima Centauri garners much attention, other exoplanets have also captured the scientific community's interest. For example, the Kepler Space Telescope has identified numerous Earth-like planets in other star systems, some located in the habitable zones of their respective stars. These discoveries prompt researchers to reassess the conditions necessary for life. Scientists are increasingly considering alternative biochemistries, such as life based on silicon instead of carbon, expanding the scope of potential life forms that could thrive in different environmental conditions, including extreme temperatures or high radiation levels. Astrobiology, now an interdisciplinary field, integrates insights from biology, chemistry, geology, and astronomy. This collaborative approach allows for more comprehensive models of what extraterrestrial life might look like. Studies of extreme environments on Earth, such as hydrothermal vents and acidic lakes, have led researchers to speculate about similar habitats on other planets or moons, such as Europa or Enceladus, where subsurface oceans may harbor life. Upcoming missions, like the European Space Agency's Ariel and NASA's Mars missions, will further investigate the atmospheres and surface conditions of these distant worlds. Mars, in particular, remains a prime candidate for finding evidence of past or present life, with rovers like Perseverance searching for organic compounds and studying the planet's geology.